now we're going to see how to actually find the parameters, create a network, and find the parameters that is training the neural network. I'm going to talk a bit about algebra. This will just be a quick overview of matrix multiplication and so on, because this helps me explain how TensorFlow is working under the hood. You are not going to need to go to that level of detail, but you can, if you want to actually implement your neural networks with all the operations. But we're going to use the Keras API that allows you to work this at a higher level. So basically, it hides all of these messy details of all the computations, and you can just tell how you want the network to be built and then train it. But I'm going to explain a bit how things work and how we are actually training the network using this stochastic gradient descent and automated differentiation. So let's start with these basic concepts and also the reason why the library is called TensorFlow. If you have a single number, we call it a scalar. A vector is an ordered array of numbers. A matrix is a two-dimensional array. And if you generalize this, a relation between any of these sets, this is a tensor. So basically, for our purposes, we can call everything tensors, scalars, vectors, matrices, whatever. And the reason why the library is called TensorFlow is because it deals with these objects. You can imagine, for example, that the parameters of a single neuron are a vector. If you have a layer of neurons, you can store all the parameters as a matrix. If you have an example, you can also use a vector because the example from your training set will be a vector of values for the different features. But if you have a set of examples, then this will be a matrix. And then you may have the examples that have more than one dimension. For example, an image may be a matrix of pixels, but also each pixel can have three colors. So it's actually three matrices stacked together, so it will be a three-dimensional tensor. If you have a batch of images, this will be a four-dimensional tensor that you are feeding into the network. So this can have an arbitrary number of dimensions depending on the data that you're dealing with. And we can call everything tensors for our purpose here, and that's what TensorFlow will do. Take all those tensors, operate on them, and move on. Things that are easy to do with matrices or tensors in general are addition and subtraction. If you have the matrices on the same side, you can just add or subtract element by element. With multiplication, matrix multiplication follows these algebra rules. So if we multiply this matrix by this one, we are computing the product of each element on this row by each element on this column, adding everything together, and then we get the result here. And then we do this for all the combinations of rows and columns. And the reason why I'm talking about this in the reviewing algebra is because you can see this is what we have in the model of the neuron. Imagine that these are the inputs, these are the weights of the neuron, and this is the value that goes into the activation function. So if you have all your examples in a matrix where each example is a row, and all your neurons in a matrix where each neuron is a column, you can do just by matrix multiplication, get all the values for all the neurons and all the examples. And this is a basic idea underlying TensorFlow, where it does all of these operations. And another important thing here is that this is trivial to parallelize. If you have a large number of processing units, for example, using graphics cards, you can spread out this matrix operation through many different CPUs, or in this case GPUs, that are each one doing one of these steps. And this can greatly speed up the computations because you are doing everything in parallel instead of one at a time. So this is part of the reason why deep learning has increased so much in popularity, because the use of specific circuitry hardware for deep learning, whether a general purpose computation with GPUs or specific circuits like tensor processing units and so on, greatly increase the speed at which this is done. So now we Using this, we can easily model these kinds of operations of passing the inputs through the neuron. And in addition to this, also, besides having the general matrix multiplications of algebra, Tensorflow also allows broadcasting using the NumPy rules. I don't know if you talked about this last semester, but basically with the NumPy library, you can do operations between different dimensions of arrays as long as the last dimensions match. For instance, you can broadcast an operation between this matrix and this vector as long as this vector has as many elements as each row of the matrix. And it will apply the operation to all the individual rows in the matrix. So you also have these operations to help work with the data. And this would be basically at a lower level how you can use the TensorFlow basic operations. For example, here we can create constants with different sizes. For example, this is a three-dimensional tensor with dimensions 2, 2, 3. This one has 2, 3, 2. And then we can do multiplications between the different tensors by calling these functions from TensorFlow. So without going into details here, the idea is that when we build a set of computations, a computation graph in TensorFlow, we are telling it what are the different steps to do all these computations, because then TensorFlow will compile this into the appropriate set of instructions, depending on whether you are using the CPU or the GPU or many GPUs or things like that. So it optimizes the computation. But more than that, it also will keep track of all the computations because of the way it needs to train the parameters. So we're going to look at that into a bit more detail. But the basic idea here is that our examples can be in batches, in groups of examples. So even if one example only has one dimension, a set of features, we will generally have two-dimensional matrices with sets of examples. The layers can be modeled as matrices of the neuron weights, and then the activation functions apply to all the values in the matrix. And all of these, the loss functions that we use and so on, are doing operations on these matrices and aggregating the values. So this is important to have this, all of these computations on the lower level done, so that we can then build the neural networks on top of this. This is something that you don't have to worry about when we are doing the assignments in practice, because you are going to use the API from Keras, which hides all of these messy details. However, it's important to understand how things work, and also sometimes if you are into some going to have to solve something a bit more specific or sophisticated, and you have to design specific operations for what you want to do, then you need to know how things work underneath the Keras interface, so that you can implement these yourself. This will not be the case for this course, but at least you know that you can do that for the future. So let's see a basic example. Suppose that we want to classify this data set, separate red and blue, and we have these very simple neurons. So we have one neuron that just receives two values as input, and these two values are the coordinates of each point. So each point in this space has two values for the coordinates. This is what the neuron receives, and the output of the neuron would be either high or low, depending on whether it's red or blue, to distinguish between the two. So the input would be a matrix with the data, a number of examples, where each example is a row here. Then we have a vector here, or a matrix with one column, with the two weights of our neuron. And if we do matrix multiplication, we get one column where we have the product of each input and the corresponding weight, and then the two things sum together. So if we multiply the coordinates of all the examples by the vector, the column vector with the weights, we get for each example what is the weighted sum that enters into the activation function. Then we can apply the activation function and get the result of the neuron for that. For example, we can use the sigmoid function, which gives us a value between 0 and 1, like in logistic regression, and this could be interpreted as the probability of belonging to class 1. So how do we determine those weights? And this is where backpropagation comes into play. We, just to sum up very quickly, so I'm not going to give much details on backpropagation, you can see more in the lecture notes, but the idea is that we have some error function. For example, suppose that we are minimizing the square of the difference between the output of the neuron and what the target value should be. This is a common function. It's not generally used for classification. I'm going to talk a bit more about that later on, but it's very often used for regression, and we are going to use that one today just to simplify things. But suppose that we have this error function, so that at the output of the network we can measure how much it went wrong. And we need to know how to change one weight somewhere in our network. Suppose that we have many layers. What we need to do is to find out how much the error function will change if we change the weight. So basically this is the derivative of the error function with respect to that weight that we have here. And what we want to do is to change the weight so that we go down the derivative of the error function. That is, we're going towards a local minimum of the error function. And to do this we can use the chain rule. So this would be the derivative of the error function with respect to the output of the neuron. And then the derivative of the output of the neuron with respect to the output of the activation function of the neuron with respect to the value that goes into the activation function, which is that weighted sum. And then the derivative of that weighted sum with respect to the weight that we're trying to adjust. So by chaining all of these derivatives, multiplying all of these derivatives together, we can find out in which direction and how much we need to change the weight in order to go slightly down the surface of the error function. And we can do this all through the network, because this would be for the last neuron on the network, but then we can go backwards through all the neurons that feed into that last one and all the neurons in the previous layer and so on. So you can imagine that we will have a chain of many derivatives on all of these different operations. But if we can compute all of these derivatives, we just need to multiply them all until we find out how to change each particular weight. So this is the backpropagation algorithm. You can see more detail on this on the lecture notes. But the general algorithm would be, we present an example to the network, we propagate the activation of the network forward, that is, we compute how much the activation of all the neurons in the first layer that receive the input, and then these feed into the second layer, so we compute the activation of those and so on, until we have everything to the end of the network, and we can compute the value of the loss function, the difference, the one that we are trying to minimize to get the output of the network close to the target values. And then we can compute the derivatives of the loss function and propagate backwards through all of those derivatives across all of the different weights. And then we can update the weights in order to adjust the weights of the network and lower the error a bit. And we keep doing this with small steps in order to improve the performance of the network. So this can be easily generalized to different architectures. You can have networks that feed on themselves and have loops. You can have networks with different operations along the different layers and so on, as long as we can compute the derivatives and propagate the error through the derivatives. So we can have different loss functions, different activation functions. I'm going to switch the order a bit on this, because today we'll focus on getting you started doing something practical. Next week I'm going to talk more about these activation functions and loss functions and so forth. So just remember, today we're going to just use the mean square error, which is the average of the square of the difference between the output and the target value, which is not really correct for classification, but it's just to simplify this first exercise. And next week I'm going to talk a bit more about those loss functions. But this can be generalized as long as we can compute the derivatives. If we can compute all the derivatives, we can propagate how much we need to change each value through all the parameters of the network. So one way of computing the derivatives would be to write the expression for all the network with all those different layers, the sums, the activation functions, and so on, and then compute symbolically the expression of all the derivatives that we want. But this would be a huge amount of labor, and it's very hard to do it in general for any network that we have. Another way of doing differentiation is using numerical differentiation. There are methods for differentiation where you take small differences in the inputs and measure the difference in the output and do it like that. But the problem with this is that it's very inefficient. You need to have to compute lots of points, especially in high dimensions, where you can have networks with hundreds of millions of parameters or billions of parameters, so that would not be practical. And also you have convergence problems because you need to take very small steps or things may blow up. So what we're doing here in the Tensorflow is automatic differentiation. The idea is that each basic operation that you're doing, those matrix multiplications, the activation functions, everything, have a corresponding derivative that we know analytically. And so we know all of these derivatives here. And since we know the corresponding derivative, TensorFlow automatically stores for each operation you do what is the derivative. So when it needs to backpropagate through there, it knows what the expression for the derivative is and uses that one to compute. So this is the automatic differentiation approach. And basically, suppose that you want to minimize the cosine of x. You want TensorFlow to do this. It will need to use the derivatives to find the minimum of this function. And when you put in the graph the cosine of x, TensorFlow includes the minus sine of x, which you cannot see very well here. This is the negative, the sine, and the multiplication of the two. So this graph express this, the sine of x multiplied by the negative sign there, and this is the gradient for the cosine function. And this is done automatically, so you're telling it to put the cosine computation on the graph, and it automatically puts the derivative there also, so that it can do backpropagation and compute the derivative for the optimization. So this is what you're doing if you want to minimize this expression, x squared cosine x plus sine x. You also have all the gradients for all the different parts and the graph of how all the gradients fit together. And this is done automatically because TensorFlow knows for each operation what the derivative is and creates the two graphs, the one with the operations that you're using and the other with the derivatives. So this is how things work under the hood in order that you can write any neural network that you want or any set of expressions. The network is only one instance of the abstract computational graph that you can use in TensorFlow. And since it stores all the derivatives, it can then optimize the functions that you want. So going back to our simple model, we can write this in TensorFlow to try to optimize the parameters there by backpropagation. And now what we wanted to do is to find the derivative of the error function. So here you can see the two parameters that we can have. This would be the loss function, the quadratic error between the predicted probability of belonging to the class and whether or not it belongs to the class. And it slides down the error function by looking at each point, at each example that we're giving, where it's going down in that surface. The colors here are not very good, but then you can see it better in the slides. And it will change the parameters. As we are moving here, we are changing the weights, and this changes the frontier here between the blue and the red. Of course, the frontier is always straight because we only have a linear combination of the two individual parameters. So the reason why this is stochastic gradient descent is because we are presenting examples at random. At each point, we are getting a slightly different direction going down that surface, and then we are updating the parameters of the network and presenting examples again and again and again. So this is the basic method for training the neural network. There are many variants. You're going to be able to use different optimizers, and the basic one, the stochastic gradient descent, only does this. Then there are others that use the gradient information and rescaling and lots of different tricks, but this is the general idea that we're going to do. So we're going to estimate the gradient of the loss function by using some set of examples. Note that in theory, what we want is the gradient of the loss function measured for the whole set of data. But if we have to pass the whole set of data every time, that may not be very efficient. And also, the average gradient for the whole set of data may end up getting stuck somewhere. So by presenting only one example or a few examples at a time, we can help kick the optimization into different places until it finds a smoother valley of the function where it ends. So the idea is that we give a small sample of the data, randomly chosen. We compute the gradient there for the loss function in that small sample, and then we update the parameters on our network by a small step, a small fraction of that direction that is going down the derivative of the loss function. So in this way, by presenting examples at random, it's going to zigzag through that complex loss function, that complex surface of the loss function, until it finds the bottom somewhere. Actually, it's not going to find a specific bottom, because you see these levels off a bit. So in general, neural networks do not converge to one particular solution. They slide down and then they kind of get lost on the plane somewhere. And if you train the same network again, you're probably going to end up at a different place, because you start with a different combination of values, and there's a lot of redundancy there. If you have millions of parameters, there are many different combinations that give the same result. So it doesn't really converge into a specific place as usual in optimization problems. It just slides down and gets stuck in some place. So another thing that we can do here, this is an improvement in stochastic gradient descent, is to use momentum. Basically, we compute the velocity of the change of our parameters as a function of the gradient. So if the gradient is steeper, we have a larger velocity. If it's less steep, it's slower. But we also add the previous velocity, a fraction of the previous velocity. So if we are sliding down in the same direction, these keep adding up, and the variation of the parameters will accelerate. If it changes direction, then it will kind of eliminate one another, and it slows down again. So this is the use of momentum, and we can see the comparison here in these two cases. So with momentum and without momentum. And you see that if it's going straight, it starts accelerating, and it's faster at reaching the end there. So there are lots of different optimizations in these kinds of search for the better solution, and I'm not going to talk in detail here. You will then maybe next week experiment with a few of them, like Adam and so on, RMS Prop, that use different techniques to try to accelerate this. But the main idea is that what we're trying to do is slide down the surface of the loss function. We are using the derivative information, but then there are lots of tricks that we can use to try to speed that up. Momentum is one example. Another example is to look ahead to see what the gradient will be at the next point, and use that also as information to figure out the direction. Other examples are to scale so that the step has always the same size regardless of the gradient. And for different networks, things can work better some ways and others. But the general idea is always using backpropagation to minimize a loss function. Another thing that is important here is how many examples we present at each time in order to compute the derivatives and update the network. And this is the batch size, or the mini batch size. The idea is that we present some examples so that we have more information about the direction to change, and also we are not always changing the values of the network. So we save time by not updating the network all the time. However, if you use a large number of examples, you reduce the stochasticity, the randomness of what the network is doing, and this then can give the problem of getting stuck easier in some places where you cannot find the gradient. So there is this bit of a trade-back there, but usually the main advantage is that it's easier to parallelize things if you take advantage of all the GPUs that you have. So if you use as many examples as the GPUs can handle, all of the operations for all the examples are done at the same time. This takes as long as doing a single example, but then gives more information to the update of the network. And generally, we use powers of 2 for the mini batch sizes, for example, 8, 16, 32, because of the way the memory in the GPU is optimized, and it makes it easier to organize things there. So in practice, usually when you are dealing with complex data like images and so on, what limits the batch size tends to be the memory you have available for storing the whole network and the examples during training, because usually a large batch size leads to faster computation. This is an example here. So if we look for each particular example, using a mini batch of size 10 or 1 seems to be the same thing, because for each example on average we have the same kind of update, but this is actually running about 10 times faster because all of those computations are being done in parallel. So even though the training per example seems to be working at the same rate, it's actually taking a lot less time because we parallelize the operations. Okay, so now let's consider a better model, because this one is very poor, the one that we found here. It's good to show the surface of the error because we only have 2 dimensions, and that makes it practical. But with only this kind of operation, we are always stuck at having a 0 input into the activation function if the 2 values here are 0. So without any additional parameter, we are limited that the line we are drawing to separate the two sets, the 2 classes, is always passing through the 0 and only rotating around that point. If we add a bias value, which we can represent like this, we have an additional weight. So we have 2 inputs, but we have an additional weight on our neuron. And this works as if it's always receiving a 1 as an input. So basically we're only adding the weight there to the function. And this now gives us the flexibility to shift the frontier to any point that we want, because now we're not stuck at having it pinned down on 0. So this would be an example. This one is always stuck somewhere around here, that is always rotating around this point. This one can start to oscillate a bit and adjust a bit more depending on where it's better to separate the 2 sets of data. So the difference does not seem great here, but it depends on where. This is mostly because the data is centered, but you can see that it's slightly moving away of the center, whereas this one is really stuck there and cannot move from that point. So another improvement that we can do is, instead of just using 1 neuron, we use 2 neurons first on the first layer, and these will respond differently because each one has its own weights. I'm not representing the bias here just to make it simpler, but each one has its own bias also. But these will now respond differently from one another to the data points. So what this one is seeing is not the original data as we have here, but it's the activation of these neurons, which represent the data in a different way. You see, they actually change the shape of the data because of how they are activated. And so when this one draws a straight line here, it can improve a lot the separation of the 2 classes, and it ends up being the equivalent of a twisted line in the original space if we undo the transformation that the previous layer did. So this is why neural networks are so powerful, because these transformations end up being the useful representations of the data for the last layer, and they are learned automatically by the network during training. We don't need to figure out how to best present the features to the classifier. So you can think of a deep neural network as a stack of transformations, so things that just change the representation of the data, so that the last linear classifier can have all the work easily done because of the representation it receives. So you can keep stacking these additional hidden layers. Each layer will give a different representation of the data, and then at the end, for example, here we have the blue points surrounding the red points, but at the end, the representation that this final neuron is going to receive makes it easier to separate the red to one side and the blue to the other, because now they are pretty much separate here. So of course, the more layers you add, the harder it is to train the network, because all of these are interdependent and they will have to learn depending on what the others learned previously and so forth. And then there are lots of techniques to improve that. But this is the general idea. You can build the network in order to stack these transformations and make the final classification easier. Okay, some details that you need to think about when using this. Some of them will be automatically done in Keras. For example, initialization of weights. We need to randomize the initial weights of the network, because if all the neurons have the same set of weights, then they will all change the same way when we do backpropagation, and they will all keep in step as if they were a single neuron. So we need to break that symmetry, and one way of doing that is randomizing the weights they have. The bias weight is not very important, but the others need to be randomized. And also, we should give them small values, especially if we are using the activation functions like this, because if we are close to 0 on the sigmoid, close to the midpoint here, we have a large derivative. So we have information about where to change the weights depending on the values that we want. But if we are away from here, the sigmoid levels off and the derivative is close to 0. And you can imagine that when we are multiplying all those derivatives, if one of them is close to 0, then all the information is gone, because now everything is 0. This is a problem, the vanishing gradients. We're going to see next week about different activations that solve this. In fact, in the optional part of the exercise today, you can use the rectified linear unit that doesn't have the same problem. But in any case, it's important to start with weights close to 0 to avoid blowing things up right at the beginning. And then this is stochastic, so you may have to you may notice that running different times can give you different results. It's not exactly the same all the time. So sometimes it's best to let things run and then go back to the network that worked best, because usually today we're going to only look at the loss in the training error. But remember, there is this problem of overfitting, so actually we need to be training with one data set and looking at the loss outside that data set to see if the network starts becoming worse at generalizing. And when we do things in practice, we keep track of the best network so far, and if we overshoot, if we train too much, then we just use the previous one and not the last one, because this is stochastic. We don't know exactly when things will end at the best point. It's also important to standardize the inputs usually, because if we are training the network with always the same learning step for all the neurons and all the weights of the neurons, if we have data that has a large range in one direction but a small range in another, by changing the weights of the different weights of these neurons with the same kind of step, we have the problem that it's harder to find a balance between the larger ones and the smaller ones. So if you center everything and you have everything standardized, it makes it easier for the network to learn. And there is an additional practical problem that when you are dealing with all of these operations, it's very easy to go outside the range where the computer can represent numbers. Remember that Usually we are using 32 bits precision, so we have a limited range for the numbers, and if we shoot outside that range, then we get an overflow or an underflow problem, and training goes bad. So if you do this, keep all things close to 0 and with a standard deviation of 1, something like that, then it's much easier to avoid those kinds of numerical problems too. We are going to use these names here. One epoch is one pass through all the training set. So typically what we do is we randomize the order of the examples in the training set, and then we present them, all these examples, to the network in batches. So this mini batch, or the batch size, is the number of examples that we are presenting at each time. And we are going to present them so that we go through all the data in the training set. This is one epoch, and then we reshuffle the training set and do this again and again and again, and usually you can take thousands of epochs to train the network, because you need to take small steps at a time so that it doesn't diverge. In general, the greater the data set, the fewer the epochs you need, because basically it's a matter of passing the examples lots of times through the network. Shuffling the data is important, because if you give always the same order, you may end up in some situation where the weights are looping and are going backwards and forwards in the same set of values, and then you get stuck. So increasing the randomness here is good by shuffling the training set at each epoch. We also need to take a bit care of the learning rate, because if it's too large, we have convergence problems at the end. The network does not go into a smooth place where it stops learning, but rather jumps around a lot. But if it's too slow, then things take a long time for it to learn. So you need to adjust the training rate sometimes. So let's see how to do this in practice with Keras. We're going to load, in this case, NumPy, just to load the data and so on, so to process. Did you use NumPy in programming last semester? No? Okay, so this is basically a library for dealing with matrices, like with MATLAB or things like that. So it simplifies that. It's nothing complicated. But it allows you, for example, to load a text file into a matrix, to index the columns and the rows of the matrix, and so forth. So I'm going to show a bit then in the tutorial how to do those things. I also wrote for the first tutorial an auxiliary function so that you can plot these kinds of things and see how your model is classified. Note that in general this is completely useless, because in practice you don't have problems with only 2 features. So you cannot do this kind of plots if you have, say, 10,000 features on your data or something like that, because you cannot plot in 10,000 dimensions. But for these kinds of toy problems that we're going to start with, it's simpler to do it this way, because it's easier to visualize what the model is doing. So I created that function just to plot. But to actually create the neural network, we're going to use the sequential API in Keras, and you create a model of this class, the sequential network. This is good for all networks that are just like a lasagna. You just stack the different layers. If you want to do more complicated networks, then you have a functional API too, but we are not going to go into that now. You create one of these, and you can add layers to this network. So we are going to use the dense layer. The dense layer is basically a layer of neurons that is fully connected to the previous layer. So if the previous layer is the input, we give the input size. In our case, it's 2 dimensions. For this kind of, you're going to use this data set. So each example has 2 values, and we have 2 dimensions in the input size. So each neuron will have 2 weights pointed at the input data, the examples. And we are going to create one layer with 4 neurons, and the activation will be sigmoid, that curve that we saw so far. And now we can stack more layers. For example, we can add another layer of 4 neurons. In this case, we don't need the input shape, because when you add a new layer, the model knows that it had 4 neurons in the previous layer, so each of these neurons will need 4 weights to connect to each of the 4 neurons in the previous layer, and so forth. So now you can just stack the layers as you want. We're going to use Sigmoid Activation, and the final layer needs to be a single layer with the Sigmoid Activation because we want the probability of belonging to one class or the other. And now we're going to train this by giving zeros or ones, depending on the class, and it will backpropagate the errors so that the network will be as close as possible to 0 on the 0 class and as close as possible to 1 on the 1 class. So to do that, we're going to compile. We're going to create an optimizer. This is the stochastic gradient descent one, the one that we saw here. We're going to use a momentum value of 0.9. Momentum it should be below 1, otherwise you're going to have problems with the convergence, it's going to overshoot. But you can put a fairly large value, maybe 0.9, 0.5, you can experiment with this. This is the initial learning rate. We can use, for example, 0.01 or 0.001. You can experiment with that to see how things work. And this is how we specify the optimizer here. Note that we imported all of these things. So we imported the stochastic gradient descent from the optimizers in Keras, the sequential model from the models, and the dense layer from the layers. There are many different options here, but these are the ones that we're going to use first. So once we have the optimizer and all the layers there, we're going to compile the model. And compiling the model tells Keras to do all that work under the hood with Tensorflow to create the computational graphs and to put all the derivatives in place and so forth. And for that, we're going to specify what is the loss function that we're going to use. If you want, you can create your own loss functions. We are not going to do that here, but you have several of them already pre-computed, and this is the mean squared error. This is a very simple loss function, which is the average of the square of the difference between the output and the target for all the examples in the batch. So it's what you do when you do a linear regression or something like that. This is not a good loss function for classification, but we are not going to complicate that now. I'm going to talk about loss functions next week. So after you compile the model, you can call this summary method in the model object, and it will give you an outline of what the model you have. So you see, we have a layer with 4 neurons here, then another layer with 4 neurons here, and another layer with 1 neuron. This non-dimension will be for the batch that you're going to feed into the model when training, which can vary in size. You can decide when you're training the model what will be the size of the batch. At this point, the model doesn't care about that yet. But it gives you how many parameters you have that can be trained, parameters that are not trained. That depends on different layers, but in this case, these are all the different weights of all the different neurons that we have here. Gives you a total of 37 parameters, and that's what the Keras and TensorFlow will optimize when you train. So now we need to train. What we do is we load this data, we separate the x, the features which are the coordinates of the points will be the first argument there, and a 0 or 1 for the class will be the target labels that we want to predict. This is the y value there, which is what the fit method will try to adjust to so that the model can predict correctly those labels. We can specify the batch size. This is the number of examples at each time it's going to present to the network before updating the parameters. You can experiment with this. This is just an example. And the number of epochs to train. I use 10,000 epochs. If you then plot the loss function, by the way, when you're dealing with networks with more than one layer, you usually find these kinds of effects because it takes time to reorganize the first layers in order for then the other ones to start to learn better how to classify things. But you can see here that maybe around 6,000 epochs would be sufficient, but since I didn't know at the beginning, I trained everything and then plotted the error to see if things went well. If, for example, we had stopped here, we could see that the error was still going down steeply, so it would be beneficial to do more epochs and not just stop them. And this you can do because the fit method gives you an object that contains the different, this history array here, or dictionary, which has the values of the loss function or any metric that you add. In this case, I'm just looking at the loss function during training, and I can plot that with pyplot. So in this case, you just import matplotlib pyplot. That part you did, right? You did plotting in last semester, or with pyplot? No? Okay, so you can do that. But that's really not complicated, it's just showing how the plotting library works. So in this way, you have a graph with the history of the loss function through all the epochs. Remember that each epoch is one pass through all the data points, and in each path, the data points are being presented 16 at a time. So 16 points, update the parameter, 16 point update. After we pass through all of those, they are reshuffled and another epoch continues. And the fit method is doing this automatically there. So that's why Keras is very practical, because all of these procedures that are always the same for networks, it just hides them from you and does it automatically. Okay, so to sum up, we saw a bit of algebra to understand how these things are then fit together by TensorFlow, and especially in the automatic differentiation. All of these operations have the corresponding derivatives, and the computational graph keeps track of all the derivatives of all the operations that we put in the computation. So then we can use backpropagation to update all the weights, because we know all the derivatives that we're using. So this, we saw this as an example of a multi-layer perceptron, which is basically a fully connected network that only works in one direction. It's a feed-forward network that is fully connected. This is a simple network that we can use just by stacking dense layers. Next week, we're going to see different kind of network, convolutional network that is used in images, and then there are recurrent networks and many different things. We're not going to cover everything, so basically we have time for this simple network, convolutional networks, and then autoencoders in the last week. But there are lots of different architectures that you can do with these kinds of models. And if you want to read more on this, you have a review of algebra and calculus and optimization in these chapters of the deep learning book. But I'm not going to require that you know all of these things for the test. This is just to help you understand how things are working. Okay?